Turn this recording. Okay.
Yes, hello, good evening. I hope you can hear me well. If you can hear me, please type in the comment section. I see we have 2 minutes left, so let's use these 2 minutes to get prepared. Am I audible enough? So, as we shall be looking at power electronics today, these are some of the things we shall be looking at, though we may not start necessarily from there. But at the meantime, I can take you through what we shall be discussing about today. So, I don't know if my words are clear. If at all you need any communication, please. I don't know, can you see what I'm writing on the board? Because I'll be using the board to explain a few things. Okay.
The board is not clear, please.
Okay, so let's try to see how we can make that work out. Thank you for the feedback. The board is not clear, please. But then so take a mouse. So I don't know, how about now? Can you see what at least I'm writing? Can you try to at least see what I'm writing on the board? If not, then I try to get a bigger font or change colors so that we can see properly. I believe some people are seeing me clearly. You can zoom in on your. I bet that you change the orientation of your phone to portrait. I mean to landscape, so that you can see me properly. So previously, what we had covered with Mr. Semuju in power electronics was simply the introductory part of it. And under this power electronics, he skipped ahead. There is a part where he talks about the semiconductor devices. That one I'm not going to repeat it, but I'm going to go straight away to what we call rectifiers. Because so far we have covered only two topics, that is rectifiers and a silicon control. Actually, SCR is part of rectifiers. Okay, so SCR is also part of the rectifiers, but these rectifiers are driven into three main areas. And under these areas, we know that we looked at what we call the half wave rectifier, and then we looked at the full wave rectifier. Okay, so in here we are going to start by looking at the half wave rectifier. We shall look at the full wave rectifier. Then we shall also talk about the silicon controlled rectifier. But as of now, we are going to start by looking at the half wave rectifier. In there, we shall have to look at some of the calculations that are involved. That is to do with the efficiency, power dissipated, and all those other small calculations that are involved in there. So when we talk about a half-wave rectifier, we know that a half-wave rectifier is simply a combination of a diode and a load. Okay, it only uses one diode to get what we call a DC output. First of all, a rectifier is a device that you use to convert an AC input into a DC output. So for a half-wave rectifier, okay, so for a half-wave rectifier, we know that we only have a diode connected inside a circuit whereby we have maybe a transformer, and then on this other side is where we have our resistor. So inside the half-wave rectifier, and you look for the circuit itself. So all this is an example of a half-wave rectifier right here, as you can see clearly on that diagram. That is a half-wave rectifier right there. So inside that circuit, you can see that we have a diode and we have a transformer on one side, we have power source on one side, and then we have a load on the other side. Okay. So when we look at that, we are going to talk about how the power changes from DC to AC, as you can see clearly. So if we have our transformer here, which is our source of AC, we know that the signal source for an AC is always going to be an alternating component for all the cycles that are existing in that circuit. So the input is going to be this side, and this is my V in. Okay, this is my input, which is V is equals to V max sine omega t. Okay, so as you can see clearly, this input here, let me say this is an end A and this is end B. The working principle is simple. During the first half cycle, which is this, when end A is positive with relative to B, we realize that the diode is going to be forward biased. And therefore, when the diode is forward biased, that means a voltage will appear across the load. So during that first half cycle, we shall all know that there will be output for that first half cycle. Then during the second half cycle, which is this, when end A is negative relative to end B, we shall all know that the diode is going to be operating in reverse bias. So this is going to be negative, this is going to be positive. So you can see directly that the direction of voltage is going to be opposite to the diode. And clearly, this is going to cause our diode to be reversing bias. So during that process, the diode will not transmit anything, and therefore it will be turned off. That is here. Okay, instead of conducting for this side, it will be turned off. And then during the other positive half cycle, still these phases are going to be reversed. This will become positive, this will become negative, and therefore the diode is going to conduct. So you realize that our diode is only going to conduct for the positive half cycles, and it will not conduct for the negative half cycles. So our output waveform is going to be something like this, and our input waveform is going to be something like this. What does this mean? That the output is only receiving power during the positive half cycles, and it is not receiving any power during the negative half cycles. Are we at par at that moment? I hope we are still together. Okay. If you have any comments, please type in the comment section. I will be able to read them out, or you can unmute the mic and speak in case you want to say something. So at that moment, I'm going to proceed and explain further on this matter. Okay. So this brings us to what we call the efficiency of this half-wave rectifier. The reason it's called a half-wave rectifier because it only rectifies during only half the cycle, and during the other half of the cycle it does not do what? It does not do anything. So proceeding there on, let us look at what we call the efficiency of a half-wave rectifier. So when we talk about the efficiency of a half-wave rectifier, efficiency of any rectifier, be it half-wave or full-wave, we know that efficiency is the ratio of output over input. Okay. So for this particular case, yes, you found us discussing about the efficiency of this half-wave rectifier. So the efficiency of this half-wave rectifier, you know that efficiency is already defined by the ratio of output to input multiplied by 100%. Okay. So what is going to be the efficiency of this half-wave rectifier? Given that we saw that our output is a DC, okay? So efficiency is going to be equals to the PDC output over the input is an AC, so the efficiency will be PDC output over PAC input multiplied by 100%. Okay, I hope my words are clear. So as you can see clearly here, that the efficiency is going to be the ratio of the DC power output over AC power input. Now, when calculating for this, we all know that power is the ratio of is the multiple of I times V, or I squared R, or V squared over R. Whichever formula you use to do, it will all give you the same results, because this is like the total power being calculated in that diagram. So when we are to look at, maybe let's say we want to look at the output DC power, okay? So I'm going to refer to the wave diagram. Our wave diagram of the output was like this. We had, it wasn't conducting for this cycle, and then conducted for this cycle, okay? I hope that end of the board is still clear. So initially, if this is from 0, this is 180, which is pi, okay? This is 2 pi and all that. But our output DC power is only contained in this half of the what? So our output power is only being contained in this half of the cycle. and not on the other half of the cycle. Okay, so allow me erase this so that I can write the equations that we need to have. So when I'm considering the PDC output, I'm going to consider the average. Remember, for DC value, we always consider the average values, okay? So definitely PDC output is going to be equals to I average times V average, okay? So that is definitely what we are going to consider in this calculation. But the derivation is simple because the average voltage here that is going to be contained in this circuit, for example, you can turn over to the circuit and let me try to get the circuit and display it for you. But the average power, that the average DC power is going to be, we are going to only use the average values, that is the current, the average current and the average voltage, okay? Then for PSC, for power AC, we shall use IRMS times V root mean square value. That's why I'm saying that for AC we are going to always use root mean square values, and for DC we are going to use average values. I hope you've gotten it. It's down. Please try to scroll. So here we are. So the average, you can see here that we are going to calculate for the average values, but the average power being contained in such a circuit is just right here, okay? Is only within this half of the cycle, okay? So if the average power is what is being contained in this half of the cycle, let us look at the board and then we proceed. So I don't know how to put it in simpler words, but we are going to have to integrate this cycle to get, in order to get the average power that is being given in that half of the cycle, okay? So let me say, let my voltage at this point, which is V equals to V max sine theta, okay? Where theta is the angle that is being changed there, okay? And for example, if my circuit of the diode had a certain, this was my RL, okay? And this was my transformer, and this is my diode. So if the diode has a certain resistance, R forward bias diode has a resistance, that resistance of diode, and RL is the load resistance, okay? The average current that is going to be flowing here, let me call it an average current, small I, okay? The average current that is going to be flowing here, okay? The DC current, which is I average, okay? It is going to give me what we call the I DC, the DC value of the current that is flowing, and is equals to, we are going to have that average value is always going to be equals to 1 out of 2 pi. Why the 1 out of the 2 pi? Because this is initially supposed to cover from 0 up to 2 pi, okay? But it is only covering pi value over that, okay? So it is going to be 1 out of the total distance it would have covered times the integral. Now we are going to integrate from 0 to pi, because our power is being only given into pi. Our curve is our curve is high for only between 0 and pi. Then times our current which is flowing, which is I, with respect to theta. Okay. So the DC value is going to be the average of the AC value of current. Okay. And the average of the AC value of current is going to be 1 out of 2 pi integral from 0 to pi of I with respect to theta. Okay. So when we reach here, we are going to look at how we can get the average value of current from the initial. Remember, this I here is the total ISC, okay? And this V is the voltage across this point if it is the secondary of the transformer, okay? So this voltage here, V, is the voltage across this point, and this I is the current flowing in that point. So from our equation of V equals to I R, realize that I, where this is my I to R total, we realize that I is going to be simply V over the total resistance RT. Okay. So with that, I will have to substitute the value of I in this equation and the value of V, which is V is equals to Vm sine theta, into this particular equation to get what is an integrable form of this equation. Okay. So, and now at the moment I don't have the liberty to write all the other side, but anyway, let me try to elongate and write that side. I hope that side is also clear. So my average value of DC current, I DC, is going to be just simply 1 out of 2 pi times integral from 0 to pi of I. What is my I is V over R total. But remember, this R total is the total resistance between this circuit. And since they are all connected in series, you realize that R total is going to be simply equal to R forward, which is the forward resistance of this diode, plus the load resistance RL. So I'll get this, I substitute it where there is R total, and I'll get V is equals to Vm sine theta, and I also substitute it where there is V in this very equation, and I'll come up with something like this. So I am replacing it with this whole thing, which is V over R total with respect to theta. Okay, so this is going to give me 1 out of 2 pi integral from 0 up to pi of my V. But what is V? V is Vm sine theta, okay, over R total, but my R total is RL plus R, okay? So I'll substitute them, R plus RL in there, but with respect to theta, okay? So when I do this, I'm integrating with respect to theta. So any equation anything that does not have theta in it is a constant. So I'll pull it out and I'll leave it as a constant. So here I will pull out my Vm and R plus RL. And what I will be left is 1 out of 2 pi Vm over R plus RL. Okay. Integral from 0 to pi of V, actually not Vm now, of sine theta with respect to theta. And clearly, now I can rub off this side. So, and clearly, we know that the integral of a sine is what? What is the integral of sine? It's a negative cos, right? So, when let me try to leave this and maybe put this away. But I hope you can still get me. In case of any comments, please type in the comment section, or you can unmute the microphone and speak. So I've pulled out my Vm and that. So I'll remain with Vm over 2 pi into R plus RL times our integral of sine, which is negative cos. So negative cos theta from 0 to pi. And simply what is left there is to substitute for the limits of 0 and pi in the final equation. So when we put in those values of 0, if we put it inside here and pi inside the equation, what do we have? We shall have Vm over 2 pi into R plus RL. Okay. Here we shall have, let me pull out the negative first. We shall have cos 0, cos of 0 minus, it is cos pi first, minus cos 0. And we know that the value for cos 0 gives us a what? Cos 0 gives us a 1. And cos pi represents 180. And cos pi gives us, what does that give us? It's also giving us a negative 1, okay? So here I have a negative 1 and here I have a 1. So negative 1 and negative 1, they become a negative 2. And this negative will cancel to become a positive. So I will remain with something like this, Vm over 2 pi into R plus RL times 2, okay? So these 2 and these 2 will die, and I will have Vm over pi into R plus RL, okay? So here the next thing that they say is that usually the forward resistance of a diode is so small compared to the resistance of the load, okay? And that will lead us into something whereby if you add these two values, they will always approximate. R plus RL is always approximately equals to RL, as we shall see. But the value that we're calculating for is the DC value of current, which is the I average, okay? So if we have I average, we can find simply so from that we have our average value of the current, we simply can relate and find our I max, okay? The equation for maximum current is just simple, and it is stated. I share that. I should try to share it. Just this. So anyway, close the window. Okay. I was talking about the value of the average current, I average, which is Vm over pi into that R plus RL, okay? So in cases whereby we need to find our this equation is going to be shall be used that to calculate in the DC value of the power, the DC power value of the power. So when we write this aside, there are other values that we need to calculate. Remember, we said that P DC is going to be equals to I average times VDC average, okay? Whereby VDC average can be given by so this value of PDC can be calculated in this particular way, and it also has another particular way there it can be calculated, where our PDC can be given by I squared DC times the load resistance RL, okay? So from this equation, I'm going to have to derive another equation for the average DC power value that is dissipated in this particular thing. So from this equation, my P DC is going to be equals to I DC squared times R L. Okay. Substitute for these two equations in this particular equation. Okay. So we shall have our IDC. Our IDC is what we got here, which we got as VM over, sorry, just a moment. So our average value, let me try to get for you the text. I don't know if it is there, but I can't see it here on the screen. But if in case you're following from your textbooks, your respective textbooks, okay? Our IDC squared. Now this value here, there is something I did mention about this I average, okay? I need to explain something about this average value here. This I average that we have got, which is going to be equal to V max over pi into R plus RL, okay? Can be related to the maximum value of current, okay? It can be related to the maximum value of current, whereby our I maximum is simply from the graph that I had drawn. Our maximum value of the current is going to be simply pi times this, okay? Pi times this, which will give us, okay, it will be Vm over pi into R plus RL, okay? But all this multiplied by pi, and this will give us a Vmax over R plus RL. This is corresponding to our I maximum, okay? So if our I maximum is that, you should always just remember that our DC value of the current, DC, is going to be equals to, simply the thing about this is that whenever you need for a half-wave rectifier, whenever you need to find the average value of DC, I mean the DC value of current or the DC value of voltage, is that you're going to get the maximum value, always divide it by pi, okay? And also, maybe if you want to get the voltage of DC, it's always going to be also equals to the Vmax divided by pi. This is something I just observed when they were doing a lot of calculations, because you realize that the DC value is always divided by pi. In actual sense, to get the averages in DC for half-wave rectifier, okay, we just simply divide the maximum value divided by pi. But which is not the case for full wave rectifiers. So we shall be seeing more and more into detail how those two things can be integrated and how they can be differentiated. But let us first go slowly, because this derivation is what leads to all these conclusions. So from that, I was telling you that our DC value of the current, our IDC is going to be simply our I max over pi, or it can also be given by Vm over RL plus R plus RL, okay? That is going to give us the DC value of the current. Then, for you to find the power, the PDC dissipated is going to be equals to IDC squared times RL, which will give me my IM over pi times RL, okay, that is squared. The reason these two die out is simply because this R plus RL is simply equals to RL, as I had stated here, that when you do this mathematics well, you realize that R is so small compared to RL, and therefore when you add them, they simply equate to almost the same thing. Am I being clear? I'm not getting any feedback from you, so I don't know. Yes, Mr. Henry, are we together at the moment? Okay, that shows that we are clear. So with these two things, I'm going to just summarize a few things down here on the side so that we know that whenever we are called across to calculate for P DC, it is going to be simply I max over pi squared, okay, times our load resistance, okay. That is one of the equations that we shall be using, and we know that IDC is equal to I max over pi, okay, and also I max can be given by V max over RL, or it can be given by I max plus V max over RL plus R, if at all the value of R has been given.
Clear.
Screen is not clear. Okay, let me try to work upon that. How about now?
Not yet.
Could it be my network? No, you put it back where it was. How about now? How are we doing?
The things are faint. I personally am not seeing. They're very faint.
Okay. Let me try to adjust. Maybe I think I'm writing very small letters, or my writing. Let me try to adjust. You give me feedback on that. I think I should first of all remove this. Can you try to put your phone in portrait and see? You try to put your phone in portrait, we see if there is some change. But what I was simply saying is that this DC value of the power, let me try to write bigger. So from our calculation, we saw that PDC, okay, is simply going to be equals to, maybe let me try to zoom in just. Take support. So you have a no? How about there? Is there anything clearer? Okay, let me try to write for you what I was saying so that you tell me, you give me feedback on that particular thing. I said that PDC will always be calculated by IM over pi, but squared times the load resistance, okay? So how is that so far? Is there any difference? Please unmute the mic and say something. Okay. I assume it's okay. Thank you. So we say that PDC is going to be calculated by that. And simply, like the way we have been doing with the bases, if you want to get I max and you have V max, I max is going to be equals to V max over the resistance across that section. In our section, we had two resistances. We had an RL and we had a RF, okay? So it will be just simply R plus RL. Okay. In case you don't have RL, R forward, it will be I max will be just equals to V max over RL. That is for the DC side. Now for the AC side, it is simple. The AC power is simple. To get the AC power, you just simply, let me try to write this side for P AC. Okay. For the AC power, is that side clear? So for the AC power, we shall always need to consider only two things. That is the root mean square value. And now the root mean square value, the only amazing thing about AC power for this particular section, whereby my circuit was something like this. We had the transformer, then our diode, okay? So I'm looking at the RMS in this secondary side. Now the way we've been calculating IRMS is different now, okay? So for this side here, our root mean square value, maybe I root mean square value, is just going to be simply the maximum value of current divided by 2, which is different from what we have been doing of getting the I max divided by root 2. Now this only applies for half wave rectifier, and it is a major point that we need to note in case we are going to make any calculations. Okay. So in case there is fine, how is that? So, I'm trying to work on my writing to see if my words cannot be faint. But anyway, you guys are not commenting, so I'm not sure. but I hope I'm clear. So I was talking about the root mean square value, and I said that for this particular kind of a system, the root mean square value is just simply the maximum value divided by 2. Even if you're getting the Vmax, the VRMS in this side, you'll just get Vmax divided by 2. That is the difference about a half wave rectifier and the full wave rectifiers or any other DC calculation. So my PSC here can be got by simply getting my IRMS value squared times the total resistance across this section. My total resistance across this section, is simply this resistance of the diode plus the resistance of the load. Okay, so this is going to be R plus RL, but this is IRMS, but it is squared. So when I substitute for that, I'll have IM over 2, but squared times RF plus RL. So when I put these two inside, I'll remain with IM squared over 4 not so into RF plus RL. We say this RF is the forward resistance of the diode. So I hope we are clear up to there. Okay. This RF is the forward resistance of the diode. So that is our AC value of the power. And our PDC, we had calculated.
Sorry, Mr. 1010. I would like to first pause the what? First pause your session for around 2 minutes and first fix the lighting. Because people, I think when I look at our output, it's not a little bit clear. Or get the information so important that you are delivering. So then you give us what you pause it up to fix what the issue of non-clearance of the screen. Thank you.
Okay, let's get a little bit of a break and then we sort this lighting thing, then we continue. About 5 minutes and then we shall be back. Hmm? Kati no take out. Neda kamera ngigyeko tofaayi. Kati take out lighting. Anti kati ndi kwagala oteekewo tulabe. Naye ate wano ng'ekifaananyi mbeera ndaba kirala. Kiri kidisplayinga ku kamera. Naye essimu ye eri ku 12 enaatera ozikira. Edda sikulaba ssebo mukama wange. Sokoleke etaala no ogigize nnyo. Ogisise nnyo. Oh, taga floodlight. So kubayo omusumaali wali tugihanginge wano. Ceiling.
Siringi ejolaba ssebo maanyi. Gikubamu ekitundu.
Ako kakuyusaamu sukuli awo. Jjukira abantu bakyali ku data waabwe. Kansooke nfune kye mbateekera sooka oyiye. Sigiteeseeyo. Ate wano ate ng'ekyuseemu. So nkisuule tulabe. Kansooke nzire. Ye ngo kano kagamba okuddayo mu date.
Oyitali mu abs.
Anti nkimanyi. Kadde kaganya okuddayo. Ogyeko gundi. Ogyeko gundi. Interface ya wane. How is that? Okay. So bana ngenda kwa meeting. Yes. Etaga giteeka waggulu. Naye basobola okusooka ne batambulirako awo. Wetulinda.
Tulina kye tulaaki.
Etaala, twetaaga etaala ebyomukisaawo teekaawo tusaba. Njagala kweyambula nzijamu so maybe I should limit on my movement. So kolete gundi essuuka nkasuuleko saagala kumanya. Kali hard light. Yaleta ekipapula. It's so hard. How is that?
To us who are here, it's okay. But the ones who are online, change it.
Can you get them to Right. Next one.
Yeah, you're making better and better.
Obakozesa eggulu ya red
Ne mark yennyini okolera
gezaako okozesa ku red aba bright ddala
Mpaako bulungi. So I'm going to unmute. Who is this? What? Bwe Gambia. Sorry. Mama muzinzi Uganda.
Kuba zino zikooye.
Waliwo okubbira omulala. Okay. And now, so I'm putting back on the microphone. Okay. So we are back. I hope we can generate a better image. Try to see how is red. These ones are fake. Extreme light. So, is this part clear? So we were trying to derivate the equations for the DC power and the AC power. And we said that we had gotten the AC power as this value here. So we want to look at the DC value of the power here. The AC power is this, and we had also got our P DC to be equals to IM over pi squared times RL. Okay, and then for PAC it included RF and RL. Now here, leave alone the derivations. The derivations I went through them because I know at sometimes they may ask you to do the derivations and to come up with such equations. But there is one thing that you always need to note. My circuit was like this, okay? And I had a diode here, and I have a resistance in DC, half of the diode. Leave alone the power which is coming this side, which I don't know about. But the power in this side, the power that is going to be delivered to the load, P delivered to the load, okay, is going to be equals to the I DC squared times the R of the load alone, okay? That's why I'm having here RL in this equation. Then someone might ask me why I have RF and RL in the other equation. The other equation is for the AC power being delivered to DC rectifier. So in this AC power, the power being delivered across this is having two resistances. It has this forward resistance of the diode, and it has this resistance of this resistor. That's why I said that the PAC is going to be simply equals to the ISC, okay, RMS, okay, times the total resistance across this circuit, which is RF plus RL. Now the technique is always simple. Whenever they give you a half-wave rectifier, the AC current is simply going to be equals to the RMS AC current is simply going to be equals to I max over 2, okay? But this is squared, remember. So this was squared. So this is IM over 2. So we shall just square it and multiply it by RF plus RL. And whenever you're working with the DC power, you simply know that the DC power, the DC power PDC is going to be equals to IDC. But IDC, I told you, you can simply get IDC being IM over pi. Then you square it times RL. So what I'm trying to emphasize is, let me maybe just try to write it aside. I hope this part is okay. But when I emphasize what I was talking about is that when I'm working with DC, I don't know if blue is clear, but when I'm working with DC, my DC average power is going to be maybe IM over pi. Then for AC, it will just simply be IM over 2 for a half wave rectifier. That is the difference. It will be okay. So, yeah. So, but you people who are online, are you getting me? I'm not getting any feedback from you. No comments at the moment. I don't know because this was intended for you, and you need to benefit from it. So, in case of anything, please make comments so that I can know what to do further. Yes, Mr. Henry, please say something.
Yeah, the video quality has been a little bit poor, and yet I'm using a 20 Mbps Wi-Fi. I don't know if problem is on my side or it's on your side.
Okay, Mr. Dema.
You speak from here.
So, Mr. Dema, you will excuse us and any other person about the image quality. We are supposed to receive some order from a specific company to supply us with a better camera, and it didn't show up. But tomorrow or for any other session, we expect to improve. We have a problem with our lighting, so you'll just excuse us for today. But we promise you a better quality when it comes to any other session to come. We are sorry for that inconvenience. Thank you.
It's all right. Otherwise, I thought the problem was on my side.
No, we are sorry.
Otherwise,
It's a
thank you.
system problem. We shall fix soon.
Otherwise, to the rest, are you also facing the same problem, or there are other challenges? My audibility, am I audible? Yes, Caroline, say something.
It is okay. It's only the things, the output is not okay. So since you promised to change tomorrow, shall keep waiting, inshallah.
Okay. Thank you very much, Caroline. But as far as understanding is concerned, are we picking something as well?
Yes, we are, though I think we are still deriving, right? Though
No.
we've not yet written the questions. So maybe you're still giving us the basics.
Yes, you're right. I was just bringing out the basics at the moment. So up next is actually we have finished the derivation part of it. We are going to see some questions, see how things are done, and then with that I believe we shall be able to answer some few. Are you saying something? Okay. Yeah. So that was what I was saying. I was giving the briefs about the derivation and all these other things. So at the moment, I'm going to try to go slowly by slowly so that I understand my qualities so bad, but as he has promised, our devices and things are going to be improved so quickly so that we avail something better. So from that, if you've been following, I believe maybe you've written down something. I will have to explain something little about to do with the overall efficiency of this system. So the overall efficiency is what we have been getting, what we have been defining, and the overall efficiency is going to be equals to the PDC that we got over PSC. Okay, and our PDC we got was IM. We said, remember, for this we just divide by pi T square times our resistance across the DC, which is the RL. Okay, let me try to use a bigger font. Sorry about that. So I was saying our efficiency is going to be given by PDC over PSC. But our PDC was simply I max over pi T squared times the load resistance RL. How is this marker? And then our AC value, okay? So our AC value was simply equals to, remember that for AC we said we get I max over 2, and then we square it times the total resistance across the load, which is RF plus RL. So realize that when I open the brackets, I'll have a pi squared. Okay, the IM and the IM will cancel, and I will have 1 out of pi squared divided by 1 out of 2 square, 1 out of 2 squared. So inside here, I'll have my IM square. I said the IMs will cancel because even though I pull them out, you can see clearly that they're going to cancel. So I'll remain with 1 out of pi T squared divided by 1 out of 2 T squared times this value here, which will have RL over RF plus RL. Now this is where what I was talking about comes into play. We said this RF plus RL, since this is small and this is big compared to this. So this and this, they will approximately be equals to the bigger value. It's like 1000 plus 1 will simply be equal to 1000. It's like you never added anything. So realize that this will equate into RL, and therefore this and this will cancel. So I'll simply remain with 1 out of pi squared divided by 1 out of 2 T squared. So with that, when you use your calculator and you put in 1 divided by pi T squared, then you divide it by 1 divided by 4 but squared. Okay, what do you get? So here I'm getting a 4 over pi squared, because this is simply going to come up. Not so? It's simple. I don't know if this part is visible. This one will be 1 out of pi squared, not so? This. Divide by 1 out of 2 squared, which is 4. So I'll remain with the 4 will go up when I put a multiplication sign, and I will have a 4 over pi squared. So when I put that in my calculator, 4 divided by pi squared I'm getting a 0.405. So this is going to be equal to 0.405, but we are going to multiply it by 100% to get the efficiency. So our overall efficiency will be 40.5%. Okay. So that gives us what we call the overall efficiency of a half-wave rectifier. Well, no matter what you do,
But we've not seen what you've written. The other side, the cameraman knows only stopped on 1 out of pi squared over 1 of a half squared. So we are not seeing the other part.
you stopped on 1 out of pi squared and
1 over 2 squared and a half squared.
Okay, I think let me focus this side of the board. So I'm going to just bring it here so that I can write it. So that side, what I wrote was simply that I will have 1 out of pi squared divided by 1 out of 2 squared. Okay. And when I do this, I'll apply a multiplication sign there. I'll have 1 out of pi squared times 4 squared out of 8 times 4. So so this is what I was mentioning, over 4. So when I do this, I will simply remain with 4 over pi squared. And when I put this in the calculator, what I will come up with is 0.405. But remember, what we are calculating for is efficiency. So we always multiply it by 100%. So therefore, after multiplying it, we shall get a 40.5%. So this one here gives us what we call the total efficiency of this system. No matter what we do, the efficiency of this system will never exceed 40.5%. So here comes the question. Does this mean that all the other power that is being put into that half-wave rectifier, that is it wasted? And the answer is simply no. The reason is, so connect this one charge. So the reason is that this is a half-wave rectifier, and it only receives power during the positive half cycle of the rectification cycle. So for a half-wave rectifier, let me put it here where it is a little bit clearer. So for a half-wave rectifier, its power, remember that the signal comes in as a full wave, but a half-wave rectifier only produces output for only half the time. Okay, so inside the wave, power is contained in equal portions. The upper portion is containing 50% of the power, and the lower portion is also containing 50% of the power. But a half-wave rectifier only caters for the upper 50% and does not utilize the lower 50%. Are we clear? So if the lower 50% is not utilized, that means it is not catered for. So of this upper 50%, only 40.5% is utilized. You get it? So if they've provided it with 50%, it is only utilizing 40.5%. That means it is having a good efficiency when you compare what it has received to what it is outputting. But the only problem is that it only receives power for only half of the full cycle of the input. So that is the reason as to why its efficiency is very low. So with that, I think we can look at a few questions and maybe see what we can answer. So I'm going to share some of the questions on my screen so that we can see how to answer them or what to do about them. Just briefly, if you're following from the textbook, please so if you're following from the textbook, you can go to page there is an example 6.12 on page 14 of the book. So let me try to share it here and we see what is contained in that. So those who are following from the book, I don't know if you've reached there, but in case you've
Which
reached
book
there,
is that?
that is chapters. It is labeled chapter 01. It's chapter 06. Chap 06. Yeah, CH06. But anyway, for those who are not with the book, I can read out the question. So if I can read out for you the question, they are just simply saying the applied input AC power to a half wave rectifier is 100 watts. The DC output power obtained is 40 watts, and they're asking what is the rectification efficiency, and they want us to explain what happens to the remaining 60 watts. I think this is just a scenario question of what I have earlier on explained. Okay. Is someone saying something?
Which page of the book?
It's page 14. It's page 14. The normal pages. Or if it is the abnormal page, you look for page 89. The reason I'm saying abnormal is because it was picked from a book. So its page numbering may differ from what we have on our screens. But it's page 89, the original. So what I was saying is that this question here is they're asking us about what happens to the rest of the power. So they're saying the applied input AC power to a half wave rectifier is 100. Then the DC output is 40 watts. They want us to find the ratio. The ratio is just simply dividing through. Okay? They're saying the applied PSC is 100 watts and the PDC output is 40 watts. Okay? They want us to find the efficiency. Efficiency, we said, is the ratio of DC to AC, which is 40 over 100, and this is giving us what? But multiplied by 100%. So this is going to give us a 40%, you realize. So the rectification efficiency is 40%. But then they're also asking us, what happens to the other 60 watts? Now, what happens to the other 60 watts is what I've previously explained. That if it was supplying 100 watts and this is the sine wave, that means if the total of the input is 100 watts, that means the lower section is having 50 watts and the upper section is also having 50 watts. So the DC rectifier is only receiving this 50 watts, and they want us to, and out of this 50 watts, it is producing 40 watts. Okay, So that doesn't mean that the entire 60 watts is wasted as heat and all the other byproducts. As you can see clearly, the explanation down there. Hey, as you can see the explanation down there, but the 60% is not entirely wasted, but only the rectifier is only receiving the 50 watts of the positive half cycle and not the other negative half cycle. So that's why of the 50 watts it is outputting 40 watts. Meaning if you're to get the overall efficiency of this system depending on the power that has been input, it will be the efficiency according depending on the power that has been received will be 40 watts, which is the output, divided by 50 watts, and this is going to give me an efficiency of up to 40 divided by 50, that is 0.8 times 100%, and this is going to give me an efficiency of up to 80%. So depending on the power that has been received on this thing, it is producing out 80% of that power. I hope that is clear. So with that, let me look at maybe another physical example that can maybe require us to do some calculation. For example, if we go and follow example 6.1 theory. So if we go to example 6. Before we go to 6.1 theory, yeah. Let's go to 6.1 theory and look at that particular example in that handout. 6.1 theory is on page, just scroll down a little bit, it's on page 90 from where you were, or page 15, just the next page. So 6.1 theory is a question. And inside this question, they're asking you about the mirror box so that we can start this question afresh. So this particular question, they're asking us, they're saying an AC supply of 230 volts is applied to a half-wave rectifier circuit through a transformer of turn ratio 10 to 1. Okay, and they're saying find 1 the output DC voltage, and 2 the peak inverse voltage. Assume the diode to be ideal. So when they say assume the diode to be ideal, that means we don't consider its internal resistance. So this is our circuit, and they're saying the voltage across this is 230 volts. Now it goes to a transformer, and the output is connected to a diode to a resistance, a load that we don't know yet. Did they give us the value of the load? No, they didn't give us the value of the load. So in that question in particular, they're saying the primary of this coil is being supplied with the 200 volts. And now we don't know, because remember we are calculating according to the secondary of this particular coil. The voltage that we are supposed to be interested in is this voltage across this point, okay, V second, okay, and clearly this V secondary can be got from the primary voltage. Remember the values they have given us here are root mean square values, okay, because remember when we're doing last time power systems, we said when they don't mention that maximum voltage, you know that is the root mean square value. So similarly, even this point here, we shall consider this 230 to be the root mean, the root mean square value. So we shall need to convert this one into the secondary voltage, and then we shall need to calculate further from there. So using V primary over V secondary being equals to N primary over N secondary. You will know that our V primary, which is 230, over V secondary, which is what we want, is equals to N primary. Our N primary is the 10 over 1. So simply when we take Vs the other side, we shall have 230 divided by 10 being equals to V secondary. Okay? So our V secondary is going to be equals to 23 volts. But that 23 volts is still the RMS value. And what are we interested in is the peak value. Now here is why it becomes so interesting again. Last time we were looking at an RMS value connected directly to a load. Now this one here, whereby in the primary they had given us this RMS value as they had given us this 230 volts as an RMS value. To change it to peak value, here they first of all converted the primary to peak value, then they took it to the secondary, which was simpler. Now for us to convert the primary to the secondary, I think if I use my formula, I might confuse you a little bit, but it is what I believed would be simple. Okay, before even you go to this 230, okay, you need to convert it directly into a peak value first, okay? But even when you reach here, you can convert it directly also into peak value by dividing it now by root 2 because it was coming directly from the mains. So VRMS is Vmax over root 2. So our Vmax, say VRMS equals to Vmax over root 2. Now someone might be confused. The other side it was IRMS being equals to IM over 2. Let these two not confuse you. This one and this one are two different things for this particular scenario. So here our Vmax is going to be equals to VRMS times root 2. The reason I'm doing this is because our primary was also given in a VRMS, and this primary is independent of the secondary. If it was connected directly, maybe we'll divide it by the way we have been dividing, but if it is being coupled across a transformer, so there is that root 2 that is coming into play. So when you do that, you have our 23 times root 2, and it's giving us our V max being equals to 23 times root 2, and this is giving us what we have as 32.5. So it is giving us a 32.5. It's giving me 526, which is 53 volts. Okay, are we together up to there? I hope we are.
Yes.
Yes, thank you. So that is our Vmax of the secondary. So if I'm to write this Vs is going to be Vmax sine theta, something like that. Is saying something?
No.
Okay. Thank you. So I was continuing with Vmax being that, okay? So let us look at what was our question actually. Our question wanted us to find, it's good to know where we're going. So they are telling us find the output DC voltage and the peak inverse voltage. Now VDC is simply going to be Vmax divided by pi. Okay, someone can just get it simply by that. Because I had told you that to get any DC value is the maximum value divided by pi. So I'm not going to follow his formula is being so long, but VDC output, VDC, is just going to be simply Vmax divided by pi, because it is the average value of the voltage in DC secondary half, and it is going to be equals to 32.53 divided by pi. Sorry? Yes. So our Vmax is that, our VDC is that, and when I do that divide by pi, I'm getting a 10.35 volts. So I'm getting my VDC. I don't know if this section is still clear. Let me go to the next and we see. So I'm getting my VDC being equals to 32 divided by pi, which is 10.3353. So I'm getting a 10.35 volts as my DC voltage. Then the next question, they wanted us to find the peak inverse voltage, assuming the diode is ideal. So the peak inverse voltage, what we call the peak inverse voltage, PIV, is simply the voltage that appears across the peak, okay, the maximum voltage that can appear across the secondary. So that peak inverse voltage is simply the maximum voltage that can appear across the secondary or across the diode. And this peak inverse voltage is just always going to be equals to the V max of the secondary, okay? Because in our cycle, remember our cycle is like this. We have an input cycle and the other output cycle, and the other cycle which is not being output. So the peak inverse voltage always occurs between these two sections. And remember that for a sinusoidal wave, if this is my maximum voltage V max, okay, this is also going to be my maximum voltage V max. The distance from here to here is the same, just that this is reverse and this is forward. So the peak inverse voltage always occurs between these two sections here. And you can see seriously that the peak inverse voltage is simply going to be the maximum voltage across the secondary. And it is going to be simply equal to what we got as our maximum voltage, which was 32.53 volts. And there we have the peak inverse voltage as that value. Any questions?
Just like that.
Yes, just like that. So let us try to see another example. Sorry? Okay. So I was saying, let's look at maybe a more challenging example. For example, should we skip forward to 6.5? Let's look at this one here, which is having an internal resistance. The next one, actually. So when we go to that next example, they're saying a crystal diode having an internal resistance RF. Now this time around, they've given us an internal resistance, but let's read through the question and then we pick some few things that we can write down so that we can see what to do with this particular question. So this question is saying a crystal diode having internal resistance RF is equals to 20 ohms. They're saying our internal resistance RF is equals to 20 ohm. And they're saying is used for half wave rectification if the applied voltage V, the applied voltage V is equals to 50 sine omega t, sine omega t, and the load resistance RL is equals to 800 ohms. Okay, so they want us to find one, the average S, the maximum. They want us to find, let us go slowly by slowly. They want us to find IM, they want us to find IDC, and then they want us to find IRMS. So that is our question. Now for this question, even you can redraw the circuit just for simple terms. Let's say now this one is not supplied through a transformer, it is just direct. We have our current coming, it flows through a diode, then it goes through a certain resistor, like that. And then they said our resistance RL, and this is RF. Now this has a certain resistance RF, and the voltage here is V. And I've told us V is equals to 50 sine omega t. So whenever they mention that the voltage is V is equals to 50 sine omega t, you know that they have given you something. So this V is the instantaneous voltage, is equals to V max, which is our 50 sine omega t. The general equation is V is equals to V max sine omega t. So our V max here is corresponding to 50. Okay, when we rewrite this equation, V is equals to 50 sine omega t.
Excuse us, Mr. Duncan. We
Excuse
need
me.
you to, yes, we will first somehow write the bigger letters on the diode, what we have written above the diode is not clear. RF, is it RF on top of the diode?
Tubadde tosobola kuŋŋamba. Wese okomawo. Yes, Caroline, you're saying something?
The screen has disappeared.
The screen has disappeared. Let me see. Let me see. Let me try to share it, but some other people are seeing it. I don't know. Maybe could the problem be there? That side.
I don't know.
Uh, okay. Let me try to stop sharing it, and I share it again, and we see. Nothing as of yet. Still,
Yes.
you can't see it.
It's now on.
It's now on. Okay.
Though you try to put big letters.
Okay. Okay. Thank you. So, but this was the data they had written. So I had just redrawn this circuit, and I was labeling my. So I had redrawn the circuit, and I was trying to label my given values. This is a diode, and this is the load, the RL. Okay. So I was giving this as RL, and this thing is having a certain resistance RF. So they had given me my RF, my small RF, which is the forward resistance of the transistor, and they have given it to me as 20 ohms. Then they have also given me my V equals to 50 sine omega t, which is the voltage across this unit. And they've also given me my RL, which is 800 ohms. So what I was trying to emphasize is that they have given me this equation, but that equation is in the form V is equals to V max sine omega t. So this V max and this, they correspond to be the same thing. So someone can clearly tell that this Vmax is the same as this 50. Therefore, my Vmax is equals to 50 volts. Okay. So that value they have given me there is corresponding to my Vmax, which is 50 volts. Now, if they've given me Vmax, they are in the question they are telling me they want me to find the I IM. They want me to find IM. They want me to find the DC voltage, and then also the RMS. So if we are always given VM, we can always find the IM. Now this is also going to be simple. You don't need to cram that formula you're seeing down there. You can use voltage and current. If the voltage here, suppose the voltage across this point is the maximum voltage, okay? The current that will flow is going to be the maximum current. And we know that from V equals to I times R total. So we can always get that if I'm using Vmax, therefore the other side should be I also max. Therefore my Vmax is going to be equals to I max times the total resistance. But my total resistance, since I'm dealing with a diode and a certain load, my total resistance is always going to be R forward plus RL. So when I add these two values, I'll have my Vmax being equals to, what am I looking for? I'm looking for I max. So I'll have my I max being equals to Vmax divided by RF plus RL, like that. So as you can see, what is left is just simply substituting for these particular values. So this is going to be equals to my Vmax was 50 over my RF was 20 plus my RL, which is 800. So when you do that, you can do the mathematics and you'll see that we have 50 divided by 820, and that is giving me a total current of 0.0609. Okay, when you round it off, my I max is being equal to 0.061 amperes, whereby you can change this into milli by taking, you multiply by a 0. So I take 1, 2, 3 times and I'll remain with 61 milliamperes. I hope that is understandable. When you take 3 times, you multiply by 10 power negative 3. So there we have our first value. Now let us look at the second value they want us to find. I hope there are no questions there. The second value they want us to find is the DC value of current. Now, I don't know if you're going to allow me to use this very part, because the other side, I don't know if it is clear. But yeah, I hope it is clear up to there. So at this point, we are going to have to calculate for the IDC. But remember what I told you, that IDC is going to be the average value of the current flowing. And for DC values, getting the average is just simply getting the maximum and you divide it by pi. So when we get our maximum value, which is IM, my IDC is going to be simply IM divided by pi. And this is going to give me my 61 in milliamps divided by pi. So when I do that, 61 milli divided by shift pi, it is giving me 0.0194, which equals to 0.0194 amperes. When you take it the other side, 3 times you multiply by 10 power negative 1, 2, 3. So it will be 19.4 milliamperes. and that will be the DC value of the current. So clearly from that point we can also find the root mean square value of the current, and for current we said the root mean square value we divide it by 2, not by root 2, which is the difference what I wanted to emphasize the other side. So for I, root mean square value is going to be equals to I max divided by 2, which is going to give us 61 milliamps divided by 2, and that is going to give us 61 divided by 2, that gives us 30.5.
Excuse me.
So sorry.
Pardon on the root mean square value. It is what?
For root mean square value of a current in a half wave rectifier, it is the maximum value divided by 2. Unlike for voltage, which was divided by root 2 the other time from our previous example that we have just done. Is that okay?
Yes.
Yes. So that's the major difference. These numbers here are supposed to be simple, but only these few things are what take us off. You may find that the root mean square value here is divided by root 2, and then the other time again they're saying divide by 2 alone, which makes it really difficult, okay? So that is the only problem here. But as long as you note this small formula here, that the root mean square value of current for half wave rectifier, again only for half wave rectifier, is I max divided by 2. That is the only formula. So here we shall get a 30.5 milliampere, and that is giving us our IRMS value of the current. So given this scenario that we have our root mean square value of current, we have our root mean square, we have our DC voltage, we have our DC current, there is a next question, the next part, which is saying they want us to find the AC power input and DC power output. Now here again we need to note, where does AC power input occur and where does DC power output occur? So the AC power output input occurs before this whole cycle. Allow me to rub this part off. So the AC power is occurring before this diode. So the AC power input is occurring and it is taking together this resistance and this resistance. So to get the AC power P, so to get the AC power PSC is going to be equals to, so PSC.
We are not seeing what you're writing.
Yes, I'm trying to figure out how to make it bigger.
No, maybe put the camera to where you've turned to.
Oh, it is the other side. Sorry.
Mm.
Okay, thank you. You try to tap on your screen and push it towards this side. Like you try to tap on your screen and then you move it to try to move and adjust to my angle. Is it doing good?
Yes, yes.
Okay, yes. So I was saying my voltage here, we're talking about the AC power, okay? But the AC power, I said, is occurring between here and here. So it is taking together all those resistances. So my PSC is going to be equals to, now PSC we use always the root mean square value of the current, okay? So it's going to be IRMS but squared times the total resistance across the section. And our total resistance is going to be Rf plus RL. So here it is also just a matter of substituting what we got the other side. We got our IRMS to be 30.5 milliamps. So we shall put 30.5. It is exponent negative 3, not so, squared times our RF. Our RF is 20 plus our RL, which is 800. So what is left is pressing those values in the calculator, and we shall have our AC power input. Have a late camera. So I was saying, so from here we can calculate for the AC power input. The rest is just simply doing what? Putting it in the calculator. So it is going to be 30.5 milliamps, but squared times what we have in the brackets is 820, and it is giving me 0.76. Okay, so it's giving me a 0.76 amps. So my PSC is equal to 0.76. Let me to 3 decimal places, that will be 763. Yes, 763 watts. These are measured in watts, and that is our AC output, our AC input power. Now similarly, to get also the DC input, our PDC. Now PDC, we look at where is the DC occurring. So the DC occurs right after DC section. After this diode, we go to the DC output. So when we reach this section, we concentrate so much on the other side, because the DC is only appearing across the load rather than DC resistor. So the PDC is going to be equal to IDC but squared times the RL, because it is only appearing across the load RL. So if it is appearing across the load RL, we know our IDC, we got it is 19.4 milliamps. So this will be 19.4 exponent negative 3 but squared times our RL. Our RL is 800. So when we substitute for those values, we have a 19.4 milli but squared times 800, and it is giving me 0.301. So it is giving me 0.301 milli. These are in watts. So this is giving me 0.131 watts. 0.301 watts. So that is our DC input power. So that is our DC input power. Next, we want to find out, the next part of the question is asking us to find out the DC output voltage.
Excuse me,
Yes.
I need some clarity.
Mm.
The power coming is SC and it
Yes.
ends on the diode.
Yes.
Okay. Then the one to the load is DC.
Yes. So when we are calculating for the AC power, that is why we are considering these two sections, because the AC appears across, it is like it is appearing across all these things here, but DC starts from here. When I'm considering for AC, I'll consider across the whole section, but DC I'll consider from here up to here. This will give me my DC. This is giving me my AC. So when I put these two sections, AC is like it is taking together this RF and RL. And then this DC, so this DC is only appearing across this section, as you can see, because DC is only appearing after the diode. So that's why for DC I'm only considering the RL, but for AC I'm considering both. I hope that is a clear explanation.
Yes.
Yes. So the next question they wanted us to calculate for the DC output voltage. Now the DC output voltage is also simply the average voltage that is appearing across that point, okay? So the DC output voltage can be given by I DC times R DC, because V equals to I R. Okay, let me go this side. So clearly we can see that our VDC is going to be equals to IDC so our VDC is equals to IDC times R DC. But R is not DC or AC. So it is R load. So our VDC is the voltage across this resistor, and the current flowing through this resistor is going to be my IDC. So that is simply the same theorem. We put our IDC which we had calculated as, what was our IDC? Our IDC was 19.4 milliamps. So it will be just simply 19.4 milliamps, which is exponent -3 times our RL, which is 800. So this will give us a value such as, when I put it in the calculator, 19.4 milli times 800 is giving me 15.52 volts. So my VDC is 15.52 volts, and that is our DC value. So 15, that is our DC value. There's something else I wanted to show you about this DC value. Okay, maybe we shall have to apply it in the next calculation. Then the last question about this section is simply the efficiency of rectification. So it is simply the efficiency of the rectification. So it is simply the efficiency of the rectification, whereby we know that efficiency is the ratio of the the ratio of DC power output to AC power input, and it is going to be simply P DC over P AC, and this is going to give me my PDC, which is 0.301 divided by our AC power input, which is 0.763. So when we do that, we can divide through, and we shall have 0.301 divided by 0.763, and then we have to multiply them by 100, of course, percent times 100%, and this is going to give us times 100. This is giving me an efficiency of 39.44. So this is giving me 39.44 or 39.45%. as my efficiency of rectification. Yes. So that is as far as half-wave rectifiers are concerned. The last number maybe you can try to do as you prepare to sleep, but simply that is what we have about half-wave rectifiers for the moment. Do I have any questions? Members, do you have any questions? Mr. Crispus, you haven't spoken anything. Can you maybe say something? Are we at par or anything? Okay.
So, Mr. Tenken, I have a question. That why does AC start from the extreme left, then the DC starts from the extreme right?
Okay, thank you for that question. So I was explaining, I was asking why the AC is starting from this side and then the DC is starting from the other side. I'm going to rub off this maybe to elaborate about that question. So this is our circuit. Like this. And this is our AC input. So the AC input is across the AC voltage, maybe the voltage of the AC is the voltage appearing across these two terminals, not so? Because this voltage here being applied is V AC. So therefore, if I rub it off like this, and I have just these two terminals like this, so the voltage across these 2 points is our V, which is equals to V max sine. It is our V, which is equals to V max sine theta or omega t. So you can realize that this V max is equals to the I which is flowing here times the total resistance across this circuit. So you get me? If I just represent this V as something like this, maybe let me put the battery like this. If this V is SC, okay, the voltage at this point is SC. Let me redraw it the way it is. It is going to just simply be that I times this is just going to be represented by a small resistance, the diode. It is going to be represented by its internal resistance. So this voltage is equals to this current times the total resistance across this circuit. That is when I'm looking at the AC component of it. Now, when I go to the DC, something changes because in DC, we are considering what happens after rectification. In fact, the DC voltage is the voltage that appears across the diode, and across the diode is from here up to here, up to this point, because this point and this point is all across a diode. So this is VDC, this is VAC. VDC is just starting from in front of the diode because it has been rectified already. So the DC value here, when I draw my voltage symbol from this side, it is a sine wave. When I come this side, it is just this. So I'm interested in what DC. So my DC is this point here, from here up to the other opposite end of the ground. So my DC voltage, if my voltage across this, it is going to be equals to the current. That means the rest of this part is no longer necessary to me because it is not DC. So I can rub this side off, and I will remind with my VDC to be the voltage across DC rod RL, and my current flowing here to be IDC. So VDC equals IDC times RL. So that is simply the difference about DC and AC.
Okay.
So,
So, Mr. Ten, thank you for your presentation. And we would like to apologize for whether we have inconvenienced with the video, the quality of the video, but we have a freshly recorded video that we shall upload on our platform, not necessarily the WhatsApp group, because these are resources that are going to be on a certain website, and we shall give whoever has attended, you will have access to that website, so you can watch a clear video, a more clear video that has been recorded. So we have a more clear video where the images are more clear, and we shall be tossing you the link for that video. You can watch the entire video from where we started to where we have ended, and I'm sure for that one everything will be visible. However, for any incoming sessions, we expect to improve our video quality, and that we made most of the experimentations during the day when we had daylight, and we expected it to remain the same way when it comes to night. But we shall have to make some adjustments. Thanks for attending, and we would like to wish you a blessed night, unless there is any question or guidance. Thank you.
Thank you so much. Actually, the screen is now more clear. Unfortunately, the session
Yeah,
is
we
ending.
also wondering why it is more clear during night when we are almost ending.
Thank you, thank you, thank you.
Okay. All right. Tomorrow we shall be meeting still for Java. We shall meet at the same time for Java. Yeah. Otherwise, thank you all for attending. We wish you a very good and blessed night. I've ended the call.
video nengigyeteredde wano eno nnyo nnyo okusaba esinga amatwalo kibadde ku kyoko kuki ku makazi
Kuba tene ya black jacket iradde erabika bulungi.